Welcome to this lesson on using C's built-in functions. As you'll learn, a function is code that performs a specific task. You've been using the printf function to display output to your screen display. As it turns out, the C compiler provides a standard library of additional built-in functions. You might use one to calculate the square root of a value or to return the absolute value. And so in this lesson, we're going to take a look at several of C's built-in functions. This is code that's already been written for you that your programs can quickly put to use. Saves you time in writing code, saves you time in testing code, allows us to take advantage and reuse other code. So let's go ahead and get started. So throughout this course, you've been using the printf function to display output to the screen, such as hello world. When C encounters a function, C will go off and execute the function's corresponding statements, do its calculations, and then return to your program at the statement that follows the function call. So in this case, we only have one statement in our program, so when it encounters printf, it will go execute that function's code, come back, there's no more statements, and our program will end. This program uses the abs function, which is built into the standard C library, to return the absolute value of a variable or an expression. The function is defined in the header file stdlib, which stands for standard library.h. In this case, you can see we've got 4 printf statements. Each printf statement is using the abs function to determine the absolute value of a specific value. Let's go ahead and run this program. And you can see that we get the absolute value of 1 is 1, the absolute value of minus 1 is 1, and so on. And so when C encounters the abs function, it's going to go off and perform the processing that abs defines using the parameter value that we pass to it, in this case the value 1. When it's done, it's going to return its result, which our program is using within the printf statement. So if you look at our printf statement, it has the absolute value of %d. For that %d, it's going to put in the value 1, and then it has is %d. For that, it's going to put in the value that's returned by the abs function, which returns the absolute value. The C standard library provides a variety of math and trigonometric and related routines. In this case, you can see that there's quite a few math functions that will allow you to do trig operations. Depending on your program's processing, you may need to calculate the sine of an angle or the cosine of an angle, and you pass that angle to the functions in radians. And so let's take a look at our program. In this case, it's looking at the sine, the tangent, and the cosine. And to get those values, it's calling the sine function, the cosine function, and the tangent function. At the top of our program, you can see that we're including the header file, math.h. That's where all these functions are defined. And so when we run our program, you can see that we pass radians, not degrees. Our angles are in radians to the functions, and it returns the corresponding result. When you perform an integer division, it's possible that you'll get a result called the quotient and a remainder. So 19 divided by 5 is 3 remainder 4. The C standard library provides a function called div that returns both parts of an integer division. And so in this case, we've got a program that's including standard lib.h, that's where div's defined, and then our result is type div underscore t. It turns out that div underscore t is a predefined structure. In a later lesson, we're going to look at structures, and a structure is a data type that contains multiple values of possibly different types. In this case, our structure contains 2 values, a quotient and a remainder. When you use the structure, you get to each one of the values using a dot operator. And so in this case, we're going to do our integer division dividing 20 by 7, and then we're going to print the result of that, looking at result.quote, which is the quotient member, and result.rem, which is the remainder member. And sure enough, when we run this program, we see that 20 divided by 7 is 2 remainder 6. And so the interesting thing about this is that a function can return a structure. And we'll take a detailed look at structures, and we may come back and revisit this program when we do. but our functions aren't restricted to only returning integer or floating point values. If you're performing arithmetic operations, you may need to calculate the value of e raised to some value, e to the x. And math.h header file defines the exp, the exponential function. And so in this case, we're using it to determine the value of e raised to the value 0.1. When we run our program, we see our result. And so again, as you start to become familiar with the C standard library, you'll find that it's got a lot of built-in math functions that are quite powerful. In our first program, we use the abs function to return the absolute value of an integer variable. In some cases, we won't need to determine the absolute value of a floating point value. And the C standard library provides the fabs function to do just that. In this case, you can see we have a variable type double with minus 3.14. Our printf statement displays that value, and then it displays the result of the fabs function, which should give us the absolute value of a floating point. And sure enough, when we run the program, it does. Now, when we do a floating point division, we typically get a whole number and a decimal point and some numbers after the decimal point. And there may be times where you just want to know where are those numbers after a decimal point. In such cases, most C compilers provide a function that allows us to get the result, the remainder result of the floating point division, and that's the fmod. And so just as mod returns the remainder of an integer division, fmod returns the digits portion of a floating point division. When C stores a floating point number, it does it using two parts, an exponent and a mantissa. And you might research how does C store floating point numbers, and you'll see how the memory that contains the floating point number is actually broken up into these two parts. Well, behind the scenes, many C compilers provide an frexp function that will return the mantissa and exponent part of a floating point number. This program goes and grabs those for the value x, which has the value 1.25. And so doing this, you can kind of see how C stores those particular components, and then how it turns those later into a floating point value. And so we can get the floating point value by taking the mantissa portion and multiplying it by 2 raised to the exponent. And so in this case, it will show us our mantissa component and our exponent component, and then we'll put it all back together to get the original value 1.25. And again, depending on your math operations that you're performing, you may need to know the natural log of an expression. And so this program uses the log function, which is defined in the header file math.h, to show the natural log of the value 512. When we run our program, we see our result. In this case, I guess we get a syntax error because value is not defined. And so let's actually fix that. And try and rerun things. And the natural log of 512 is 512. It looks like we're screwed. Depending on the arithmetic operations your program is performing, there may be times when you need to calculate the natural log of a number. To do so, you can use the log function that's defined in the header file math.h. In this case, our program is displaying the natural log of the value 512. When we run our program, we see our result. And so key things to note is we're calling the function log, and when we do, it returns the value that's being used in the %f portion of the printf statement. In a similar way, the log10 function, also defined in math.h, returns the log10 of the value that it's passed. And so let's take a look at a couple examples. Let's run our program. And we see that log 10 of 10 is 1, log 10 of 100 is 2, log 10 of 3, or 1000 is 3. So 10 times 10 is 100, 10 times 10 times 10 is 1,000. And again, when we deal with floating point numbers, there may be times when we want to break the number into its whole part and its fractional part. And so in this case, we have the number 5.4321, and we've declared variables whole and fraction, and we're going to use the mod f function that's part of the standard C library defined in the header file math.h to get those values. And so when we run this program, it would show our whole part, 5, and our fractional part, 4321, in their component parts. It does that by assigning the return value of the fraction, in this case 4321 part, to the variable that's the function's return value. And you can see that we're passing an address, and we'll deal with address and parameter changes in detail later in another lesson. But to change the value of that parameter, we have to pass it by address. And sure enough, when we run this program, we see the following output. And so there may be times when we want to calculate the value of 10 raised to some value. In such cases, we can use the POW10 function that's part of the standard C library that's defined in the header file math.h. And in this case, we're looking at 10 raised to the minus 1, which gets us a decimal component, 10 raised to 0, which is 1, 10 raised to 1, which is 10, 10 raised to 2, which is 100. And so using POW10, we can calculate these values. Now, depending on the processing our program performs, maybe we have a computer game or something, we may need to have a random number. And the C standard library defines the rand function, which returns a random number. And so in this case, we're using the header file standard lib.h, that's where the rand function is defined. And then we've got a loop that's looping from 0 to 5, just displaying the random numbers that are returned. And sure enough, we see the random numbers. Now, when we run a random number generator, we need to be able to test our code. And so when we calculate or get random numbers, they'll typically start with the same set of random numbers over and over and over until we do something that's called seeding the random number generator. And so if we want our programs to return the same random numbers so we can test and just kind of see, okay, we got this random number and this is what happened, and we don't want a new set of random numbers because we're testing, we can seed the random number. In this case, we're seeding it with 0, so we repeatedly get the same random number. So if we run this program, we'll get a series of random numbers. If we run it again, because we're seeding the random number generator, we should get the same number random numbers. And so the random number generator, using the seed in this way, allows us to repeat. Let's do it right here. And so we keep getting the same random numbers over and over because we're seeding a random number generator. Now, when we truly want a set of unique numbers, we can seed it with a random number or something that's going to be different each time our program runs. In this program, we're getting the current system time, which is expressed in seconds since January 1, 1970. And so each time we run, those seconds will be different. And so if we seed our random number generator with something that's going to be different each time, as we generate random numbers, each time our program runs, they'll be different. A common operation our programs need to perform is to calculate the square root of a value. And the C standard library provides the square root function. It's defined in math.h that does just that. When we run this program, we see that the square root of 25 is 5, square root of 100 is 10, square root of 3 is 1.73. And so using the square root function, we can quickly calculate these results. Now, most operating systems will store the current system time relative to the number of seconds since 1/1/1970. Some people call that the epoch. And so in this case, we're using the time function that's built into the standard C library, defined in time.h, to get the number of seconds since January 1, 1970. And so let's go ahead and run this. And sure enough, we see the number of seconds. If we wait a few seconds and run it again, we'll see that number increment. which it does. Many times our programs will need to know the current date and time. And to do that, we can use the seconds function, or get the number of seconds since January 1, 1970 by calling the time function. And then if we want to convert that time to a meaningful ASCII display, we can call cTime, passing the value to it. And so let's go ahead and run this. And we can see that the current date and time is January 30th, and we have the corresponding time. And so we'll find that these are relative to the current system time, may be offset based on daylight savings time or based on your time zone. And we'll see that there's a way to tell the operating system using an environment variable what time zone to use. And then the time functions that are built into the standard library will check to see if that environment variable exists, and we'll adjust them accordingly. When our programs run, there may be times where we want to delay 5 seconds, 10 seconds to post a message and then continue our processing. And years ago, people would just simply loop I equals 1 to 1,000 or I equals 1 to 10,000 to implement such delays. But processors are so fast today that that doesn't work. And so one way that we can do it is to go out and get the current time in seconds and then repeatedly loop, getting the time until the number of seconds that we desire have passed. And so this function uses a do loop. And so we start by saying we're starting to delay. We go out and get the current seconds. Then we start our do loop, which gets the end time. And as long as the end time minus the start time hasn't been 5 seconds, we keep looping. Once 5 seconds occurs, we end. So let's go ahead and run this. Starting delay. And finally done after 5 seconds. So using the time function, you can implement a delay within your code. And so we talked about the fact that you can get the current system date and time, and it's going to return those times, but the system doesn't know your time zone or if you're in daylight savings. And so most operating systems allow you to create a TZ variable, which gives you, which specifies the time zone information. And when you use those, you can call the local time function, and it will go out and grab that variable and apply the time correctly for the time zone that you're in. And so let's go ahead and run this program, and it displays our date and time. Now there's a lot going on in this program, and it turns out that the functions are using structures, and we're going to look at structures in detail in another lesson. And more importantly, it turns out that they're using pointers to structures, which means you're passing the address. And a structure is a variable that can contain multiple values of different types. And so in this case, we've got the seconds, we've got the hours, we've got the days, we've got the years. And so to get to those, when we use a pointer to a structure, we use the dash greater than that looks like an arrow. So we're looking at current date.month, and or current date month, and current date day, and current date year. And so we're using the structure. We're going to revisit this routine when we examine structures in that lesson. And so we've looked at a variety of date and time functions, and it turns out that to simplify things so we don't have to take time zones into account, a lot of times we'll store things relative to the Greenwich Mean Time. And the C Standard Library provides a function, gmTime, which returns the current system time in Greenwich Mean, and then we could apply our time zone correctly, or maybe we just want to make sure that values are being stored consistently. And so say we have a web app and users are running the app in Los Angeles and they're running it in New York, and we're wanting to log the time that somebody does something. Well, if we just grab their system time and store it, an action that took place in LA could, in theory, look like it took place earlier than one in New York. And so by using the Greenwich Mean Time, we're using a consistent time through our applications, and we can avoid such errors. So to display the current system date and time, we've been getting the number of seconds since January 1, 1970. There may be times where we want to convert a date to the number of seconds. Maybe we want to compare two dates. And so rather than trying to compare the month, day, and year, we just want to convert them to seconds and see which one's bigger. And so to do that, we can use the mktime function that's built into the C standard library. And again, it's using a structure, and we're going to look at structures in detail. And so I'm going to delay the actual explanation of this code until then. I want you to know that the function exists. Let's go ahead and run it. And you can see it, we've converted our date and time to the number of correct seconds. But we'll come back to revisit how we use the dot operator to access the structured fields in a future lesson. So what are you going to learn next? C programs make extensive use of character strings, such as hello world, to display messages. You've learned that C stores strings as a character array using the null character to mark the last character in the string. So when we have a function call that says printf hello world knows it just got a bunch of characters and it's going to keep displaying them until it encounters the null. In the next lesson, you're going to learn to start to perform your own string operations, declaring your own string variables, looping through them to show the characters, looking for that null character, and so on. Strings are critically essential to C applications, and so the next lesson will give you the foundation you need to manipulate strings.